And when we're talking about Wi-Fi and the rest of the network, what we're talking about is the stuff obviously above the link layer in the TCP/IP model, or the layer 1 and layer 2 of the OSI model. So we're going to be talking about those things and how they can impact Wi-Fi. Now, the reality is they impact any kind of network that we're using at layer 1 or layer 2. But there are some scenarios where there are some unique impacts related to Wi-Fi because of the nature of Wi-Fi. So that's what we're going to be talking about. Now, to begin with, a reminder, earlier in the week, we talked about the TCP/IP or DoD model, hourglass model of the architecture, which basically says that it gets narrower toward the middle of the hierarchy and wider at the top and the bottom because of the multiple protocols that are supported at the top and the bottom, and not necessarily because the spanning layer is not somehow important or doesn't have any complexity at all. But the goal is to reduce the complexity in the spanning layer as much as possible. When we're talking about how Wi-Fi is impacted by the rest of the network, what we're really focusing on is all the stuff above the link layer in the TCP/IP model. So this can include our application layer protocols, TCP and UDP functionality, and IPv4 and IPv6 functionality. Now, a very important thing to keep in mind is that when you're looking at vendor recommendations or test studies, blog posts that people make, research articles, anything like that, and you see the term throughput, you need to know what they mean by that. And sometimes they tell you, sometimes they don't. But there's technically this term goodput, which might be what they mean when they say throughput. So we can define throughput as how many packets have I sent onto the network. Whereas goodput, using that same definition context, would be how many packets that I sent were received. So there's a difference in that perspective. And then there's another perspective. So throughput might mean how much total data got through, whereas goodput would mean how much user data got through. So what do they really mean? Sometimes they're really meaning goodput when they say throughput. And sometimes they're meaning the green definition of goodput that we have here. And sometimes they're meaning the orange, and or kind of looks like brown too. But anyway, it was orange in PowerPoint when I selected it. And so the issue is finding out what they mean. And you kind of have to look for hints throughout the paper, the blog, the vendor literature, whatever, to find out what they're talking about. But it certainly does have an impact on your understanding of what they mean by their suggestions. So kind of watch for indicators as to what they mean. We generally, in common day-to-day discussions, we don't really use the term goodput that much. We mostly just talk about throughput. But a lot of times we actually mean goodput when we say throughput. To give you an example, technically, when you get down to the nitty-gritty details, if you're meaning by throughput things that got through to the end, when you send information, it got from you to the target end device. If that's what you mean, then your definition of throughput is this first definition of goodput. But there's a technical definition of throughput that is referring to what am I pushing out of my device? And there's no reference to, does it actually reach the destination? Was it dropped by a queue somewhere along the way in a router? And did I have to eventually resend it? And so throughput could mean both my initial transmissions and my retransmissions, that as far as my NIC is concerned, that's my throughput, the amount of data I'm pumping out of my adapter at the physical layer. And so you have to pay close attention to see what is being referenced, because it can throw off some of the quote unquote findings of different research and different studies and even different vendor reports. You can sometimes make things look better by using a different definition of throughput. I'll just put it that way. So you have to understand what they're talking about to really understand the ramifications of the information for your use and your implementation in your real world that you live in. Now, then TCP congestion control is where we're going to start. No, this is going to get good. We're going to get detailed as we go into this. Now, TCP congestion control is really often overlooked. And let me say one thing right here at the start. TCP is not TCP is not TCP. And what I mean by that is there's a wire image of TCP. So what we mean in networking protocols, when we talk about the wire image, is what does it look like on the wire? So take the TCP header. There's information in the TCP header. And that information can be seen on the wire, assuming it's not, encrypted with IPsec or something like that. So assuming it's not encrypted, you can see the bits on the wire that makes up TCP. But those bits don't tell you at all how TCP is working in the end devices involved in that communication. Now, remember, we talked earlier in the week about the concept of the end-to-end argument and the shared fate principle within communications. It's part of the internet architecture. It's part of how all of this is designed, whether it's on the internet formally or on our network that's using the internet protocols. We still have this concept. And basically it's saying that the two end devices are really in charge of delivery assurance, of retransmissions, of all of these components when it comes to end-to-end communications. And so the reality is that our congestion control algorithms are important to be understood. And actually, it was just mentioned in the comment that, Quick is going to be used later. And we're going to talk about that later on. And it's important to know that, guess what? There are congestion algorithms inside of Quick as well. They're not the same, and it's worth studying those as we move toward that as the application layer model that is certainly seeming to take over in the coming years. But the same kind of concepts are there that we need to understand with congestion control. So what we have, whether it's TCP or it's Quick over UDP, we have different things going on at the two ends. Meaning that one device might be using some different algorithms than the device at the other end is using. And a device might use a different algorithm in one of its connections than it does in another of its connections. So for example, a Windows device can use what is called automatic congestion control selection. And what it does is it picks a template of parameters for TCP communication. So these parameters are going to impact the window size, the initial window size, the maximum window size. They're going to impact the congestion algorithm that's used. These templates are going to impact all of that, right? And the system can select one template, like Windows has one called the Internet template built in, and another called the Data Center template built in. And it, for some connections, might use the Data Center, and for some, it might use the Internet template. And so it's going to change even for that same end device to be different in its functionality. So how does all this stuff work? How does it actually do it? Well, it learns from the network. And one of the first things it's going to learn is the MTU and MSS information. So the MTU, or maximum transmission unit, is the maximum size effectively that an IP packet can be to traverse the network, but it's based on the payload size of the link layer that might be across that network, right? And so remember, everything is ultimately sent from one device to another. And it's done this multiple times to get from your computer to the cwnp.com web server, right? So that's not happening on a global scale as if we can just pretend all the rest of that's not happening. It's happening from device to device. Literally one device talks to another device. So that connection you have between your computer, whether you're in Europe or Asia or the United States, and the CWNP web server, which who knows where it is in the world, right? Then that connection happens by using multiple link layer connections or layer 1, layer 2 connections between two unique devices all along the path. We call those hops, right? That we pass along to get from the source to the destination. And so you're not directly connected to any of the things that you use on the internet. You have a hop between your device and your router on your local network, and maybe multiple routers between you and the internet gateway. And then all of the hops across the internet, and then whatever hops exist on the remote network before you get to the real eventual server. And along the path, there can be different constraints on what that payload can be. And that's where a concept known as the path MTU discovery comes into play. So this is going to take advantage of receiving responses that say fragmentation is needed from different hops along the route, specifically different routers along the route. And based on the fact that fragmentation is needed, the sender can know that its MSS or MTU is too big. And by the way, the difference between the MSS and the MTU. So the MTU derives from the payload of the link layer. So with Ethernet, normally, that's going to be 1,500 bytes. Then IP has its overhead. So with IPv4, for example, you've got your minimum overhead of 20 bytes. With various IP options, you could possibly have bigger, but let's just stick with 20. So that takes us down to 1480. And then TCP has its own overhead. Assuming no extra options, it's 20 bytes as well. So we're down to 1460. So we've got 1460 as our MSS. But that's assuming that all those individual connections all along the route can handle a 1460 byte TCP segment and have the proper matching TCP headers and IP header overhead and all the rest, so that we don't get a fragmentation needed message coming back to us from some remote network. And so the congestion control needs to understand this, needs to learn this, so that it can effectively adjust things on the fly, right? So this is where we're learning from the network. Then we have our round trip time and retransmission timeout. So the round trip time is the latency from end to end, the processing delay at the other end, and then the latency back end to end. That's going to be your total round trip time. So latency is effectively the accumulation of all delays in the link, and therefore round trip latency would be the accumulation of all the links in both directions, which it could potentially follow a different path on the way back than it uses on the way out, right? That's the nature of the beast of this seamless layer at IP. And so the delays include processing delay. So that's the amount of time it takes to make a decision and take an action. It includes the transmission delay. That's how long it takes once it decides to transmit to actually get those bits out the NIC. Then there's the propagation delay. That's how long it takes to go on the link from one NIC to the next NIC. Then there might be queuing delay. So that's extra delay because the packet sits in a queue on a router for some period of time before it gets sent out. So we've got processing delay, transmission delay, queuing delay, propagation delay. And then, of course, at least hopefully, the longest processing delay might be on that remote end device before it decides to send back the acknowledgement that it has received a TCP segment. So you put all that together and you get your round trip time. That information is used to calculate the retransmission timeout. So for example, I just mentioned the acknowledgement getting back to me is what is the final result or time period for the round trip time. So the question is, what am I going to use that for? And how am I going to decide when to retransmit if I don't get an acknowledgement? That's where the retransmission timeout comes into play. And the reality is that to calculate our retransmission timeout in TCP, we don't just look at a single round trip time. We do what's called smoothed RTT or smoothed round trip time. So over time, we have a formula that we're not going to get into today, but a formula that we calculate or use to calculate a smooth round trip time that is based on a moving average of what RTT looks like over time. so that we're not just looking at the round trip time and immediately making adjustments for congestion that's going to cause us to keep hitting a wall and just having to throttle back too frequently. And that's your retransmission timeout then. How long do I wait before retransmitting based on that? But that's not all. We've also got the bandwidth to look at. So bandwidth represents the maximum data transmission capacity of a link, but for TCP congestion, we're more concerned about the maximum data transmission capacity of the whole network path and not just the local link. So, I might have a gigabit link to a switch or a wireless LAN router in a home environment. But that's just my local link bandwidth. That says nothing as to the bandwidth that I'll have going across the internet. Now, that local link bandwidth should be higher than what you're going to have across the internet so that you can push and pull the maximum that you possibly could. You certainly don't want, on modern home internet connections, for example, you don't want a 10 megabit connection between your device and your internet router. And the same is true on your enterprise networks. So you want to balance those local connections, at least when it comes to internet connectivity performance, in such a way that you can do that. In an enterprise environment, the reality is your internet pipe is usually going to be significantly less than your local links anyway. But in a home environment, I've actually seen situations where people are using really old equipment and they wonder why they're not getting good performance, even though they upgraded to a faster ISP connection, and they're still using a 10 megabit hub. I've literally seen it. So it's pretty wild. But in enterprise, hopefully we're not making that poor of a decision. And so the bandwidth is a factor too. So how do we figure bandwidth out? We have to do some kind of probing, right? And so what that means is we're kind of pushing the limits and seeing when do we hit it. That's what we mean by probing. So we're really trying to find out what we can accomplish. And then when we're being told, hey, your data's not getting through, your frames are dropping. How are we being told that? We're not getting acknowledgments back. So because of that, we know, or we assume that there's some kind of a bandwidth issue in the network. And remember, the bandwidth on a network path is not just related to any of the individual link speeds, but it's related to the fact that multiple different endpoints might be trying to get through that router all at the same time, or not might, but are in most cases. And so there's a practical bandwidth limit that I have, regardless of what the link speeds are all along the path. And what we do is we create this thing called bandwidth delay product, or BDP. And this calculates the maximum amount of data that can be in flight simultaneously. And what does that mean? Well, it means how many TCP segments can I have transmitted onto the network before I get acknowledgement for any of them that I've sent so far. That would be an example, though a bit of an oversimplification, but an example of what this in-flight means. So in-flight means I've sent it, but it hasn't been acknowledged yet. And so there might be this assumption when you first start studying TCP/IP where you think that, you send a TCP segment and you get acknowledged. And that's one of the first things you learn, right? That TCP segments are acknowledged. And so you think, okay, I'm going to send one, wait for the acknowledgement. When I get it, I'll send the next. But that's not the way it works. That is where you misunderstand because you haven't gone on to the next level of learning, right? To learn about windows, TCP windows. And so we are going to indeed send more. But we'll talk a bit more about how this BDP is calculated when we move on. And so the window and window scale are the next step in this process, which we'll also talk about more. But this basically is what we use to decide, ultimately, in relation to what we've learned about the BDP, how much can we have in flight at a time? And then we're going to set that through the window size. But there are different window sizes. So there's a receive window and there's a congestion window. So people confuse these a lot. They assume that the receive window, which is what is actually communicated in your TCP headers. So the window field in the TCP headers, and then in conjunction window scaling in TCP options, if that's being used, that is not the window that an end device is using for transmission. That is actually simply the maximum that remote device is telling you it can receive. So it's saying, hey, this is what I can handle. That doesn't mean the network can handle it. So there are rules for what can actually be used with the window, and they must be accommodated by the congestion control algorithms. And we'll get into that when we talk a little bit more about windows and window size. So how does TCP take all this input, MTU, MSS, PMTUD, RTT, RTO, bandwidth delay product, window and window scaling? How does it take all of this and adapt to change? It does it with congestion algorithms or providers. Now, the actual IETF standard for TCP says that the congestion provider must do slow start and implement congestion avoidance. And then it suggests that they use fast retransmit and fast recovery. Slow start means just start low. That's what slow start means. It means start low and then grow. It does not necessarily mean that you are not going to be moving up fast. So what I mean by that is, just because you start slow doesn't mean you increase the size of the window slowly. It means you start slow. So the moment of start is slow, AKA 1 MSS. That's normally the interpretation of slow start. So the first the starting point is 1 segment size. And then we end up adding exponentially. So we go from 1 to 2, 2 to 4, 4 to 8, 8 to 16, etc. So that's slow start. Slow start doesn't mean grow slow. It means literally start slow and grow that. And then congestion avoidance is about the fact that if we detect what we assume is congestion, then we have to have some rules that are going to govern that. Now, the standard specifies a few guidelines, but there's a lot of flexibility in it, so it can be adjusted. And remember, what the standard explicitly defines is the wire image. What goes on in the memory of that end device, it may or may not comply with the standard. There's nothing that keeps it from discarding the standard. There's nothing that keeps it from discarding the slow start rule, because there's nothing in the wire image that would break because I immediately started sending maybe with 15 segments in my very first transmission. So there's nothing that would make it where that's not going to be able to get through the network, right? But if it's compliant with the standard, then it's going to do slow start and then implement congestion avoidance. And we'll talk more about congestion avoidance protocols in a moment. And then fast retransmit means that we're going to end up detecting packet loss through duplicate acknowledgments. Basically, we receive 3 duplicate ACKs, and then what happens is the sender immediately retransmits and just presumes that there's a lost segment. And then fast recovery avoids returning to slow start. So if we get into a situation where we have these duplicate ACKs and we do a retransmission, we don't automatically go all the way back to slow start. We go to some other level instead of that. And what that usually is that we reduce the congestion window size by half. Wherever it's at, we break it in half and then start growing again from there. So in a stable network, which means a local area network, for example, in most local area networks, if you monitor this information by doing a packet capture and then looking at the information moving through the network, you would be able to find that there's a growth in this congestion window, and then it pretty well stabilizes over some given transmission window, like maybe 30 seconds of transmission. And the reality is that you don't see it going up and down heavily. But when you're going across a less stable network, like the internet, you can see the congestion windows bouncing up and down and all over the place. And that's because there are dynamic changes in the environment. Now, in addition to these minimal requirements of the standards for TCP, you have congestion algorithms that define this congestion avoidance part more specifically, like Reno and New Reno, compound TCP or CTCP, data center TCP, that's a Microsoft one, Cubic and BBR that Google gave to us and so forth. So these are all common different congestion algorithms that might be implemented. And they work in different ways. They have different mathematical calculations that they use, different metrics that they measure in different ways with different weighting to make their decision. And they do make a difference. We're going to see that explicitly here in a minute. They make a difference in the performance you get. So what is this bandwidth delay product calculation I talked about? Well, basically it's the bandwidth times latency. And the latency we're looking at is the round trip time latency. So for example, if we have 100 megabits per second and a round trip time of 100 milliseconds, which would be really long for a LAN segment, but not necessarily all that long for an internet communication, depending on what you're doing. Then what that gives us is 100 megabits per second or 100,000 kilobits per second or 100 million bits per second. 100 million bits per second times 0.1 is 10 million bits per second. 10 million bits per second divided by 1,000 is 10,000 kilobits per second. 10,000 kilobits per second divided by 8 is 1,250 kilobytes per second, or 1,250,000 bytes. So in other words, our bandwidth delay product is 1,250 kilobytes per second. So why do we care? Well, the receive window and congestion window should ideally be equal to BDP. So in this case, our receive window or congestion window should be 1,250 kilobytes. Now you can figure out what it is for a given TCP segment in a decode in Wireshark, for example, by looking at your window size and your window scaling factor, and you can put those together to understand what the size is for the receive window. The congestion window is never transmitted. You never see the congestion window on the wire or on the wireless. It's never transmitted. That's managed internally. So to understand that, you'd kind of have to look at the flow of information across the network and measure what it's sending out versus acts that are being received. And from that, you can do get some good understanding for how much it's allowing to be sent. And you'll see that grow. So you might see one or two segments sent, and then there's this pause, which not much of a human pause, but a network pause of a few dozen milliseconds or less. And then an act comes in, and then instead of just two segments, maybe you see four, and then an act comes in, and so you begin to get a picture for how it's growing. Now, it's not hard and fast like that, because the reality is that you can have acknowledgments that come back while things are in flight, which acknowledge only a portion of the things that are in flight. So to help you understand this a bit, let's just take a look here. And this is in the CNAE course, and I'm just using this because it's already in there and helps us to see it. So here's the sliding window simulator in CNAE, and we're going to bump up our segments, and we're going to slow this down so we can see it working slowly. But basically, we send a segment, and the receiver acknowledges it. And you can use selective acknowledgments. We're not going to get into those levels of detail today. But you see the sliding window moves across. Well, this simulator is showing how the window's moving. So we've got a collection of 30 segments that we're trying to send, right, to get our full communication through. And the reality is that at any given time, unacknowledged, we've got right now 10 through 14, and then 11 through 15, and so forth, that are going across the network. And so this window that we see here, this sliding box, is our window. Well, in an actual implementation, you would also see that window might get bigger or smaller. as things are moving across the network. So it's not just that the window is moving across your total number of segments, but the window might be getting bigger. More things can be in flight, or it might be getting smaller. Fewer things can be in flight until this entire communication of multiple segments gets through. And so that's what I'm talking about when I talk about the importance of this bandwidth delay product, understanding it so that we can use all that we can. So basically, the sender is going to use the minimum of CWND or RWND. So remember, RWND is what does get communicated in the, for example, the three-way handshake. When you first establish your TCP connection, then you're going to communicate the receive window. Then that's the window that's in there. Each end device is communicating their receive window. But the CWND is that variable thing that's going to change over time depending on congestion that might be assumed to be happening on the network. Now, this is most impactful in the end for what are called long fat networks. Yes, that's the thing, LFN. And basically it means we have high bandwidth, but it's a long distance. So again, the round trip time is what impacts how much can be in flight, right? And so obviously my pipe can be really big, but my pipe runs for miles and miles, or thousands of miles when you talk about internet connections, right? Then the reality is that that's going to impact the size of my congestion window that comes into play. Now, also the other thing that impacts this is the window size and window scaling, right? So the window itself is a 16-bit value. So 16 bits, 16 ones and zeros, can have from values from 0 to 65,535. Now, to be explicit about this, we would say that X can have a value that is greater than or equal to 0 and less than or equal to 2 to the power of 16 minus 1. Or we can state it in integer notation and say that X is a set of the whole integers where X has a value of greater than or equal to 0 and less than or equal to 65,535. However you want to state it, your values are 0 to 65,535. This is the number of bytes for the receive window. Now, original TCP, that's all it had. And by the way, we can go a little bit further and say original TCP IP, because there was no separation of IP and TCP. So basically, what we did is we, over the years, realized, 65,000 bytes isn't enough with higher bandwidth networks. And so we need to have a way to grow this. And that's where window scaling came in. It adds a scaling value between 0 and 14. Now, the specific reason that the maximum value is 14 is because the sequence numbers are 32 bits. So TCP sequence numbers are 32 bits. And the reality is that means we'll exhaust that pool with a certain number of segments. And if we let window scaling get too large, it's possible you'll get into a window sequence cycle problem where you're cycling back to reuse a sequence number within the window. And so we can avoid that by making sure that we never have a window scale larger than 14, which basically limits our mass window size, the biggest window size possible, to around a gigabyte. So it's still pretty big though, okay? And you don't usually see it being a gigabyte in most situations. Though in a data center, it's possible you could get close to that. So this is a power of 2 multiplier or a left shift for the window size. So remember, the maximum window size is 16 bits, all set to 1. So that's 65,535. So we're either going to take 65,535 to the power of 2. So how many times are we going to do that? If S is equal to 1, then we're going to do it just one time. If S is equal to 0, we're going to do it none times, right? If S is equal to 2, then we're going to double it twice. So 65,535 times 2 times 2, and so forth, up to a maximum of 14. Another way you can do this, which is a really cool little trick at the binary level, is to understand that if the window size is using scaling, it probably means we want more than 65, 535. Well, if you do have 16 ones, then if your scaling factor is 1, then all you do is add a 0 to the right side of those 16 ones. That shifts them all to the left by 1, but it puts a 0 at the end. So if you take, for example, 16 ones, and then you put 14 zeros to the right, shifting all the 16 ones to the left, then you're going to end up with a new value of 1,073,709,056, which is the maximum that you can get to with a 65, 535 window and a scaling factor of 14. So it's kind of interesting that the left shift concept is a quick way to play with these values and see how they work. And you can test that out for yourself. Just, bring up your favorite binary calculator that converts from binary to decimal and put in 16 ones and see what it equals. It'll equal 65, 535. Put a 0 to the right, and you'll see it's now equal to 131,070. And so instead of doing the times 2 times 2 times 2 times 2, if you want to calculate it, then of course, Wireshark does it for you. But if you want to calculate it because you're a glutton for self-punishment, then you can plug in 16 ones followed by 14 zeros, convert it, and you will see, I'm telling you right, that's the way it works. That's called the left shift in binary. And it's one way this is calculated. So what we see then is that we've got a window that slides. Okay, it moves forward in the total number of segments we need to send, and that window itself can be bigger or smaller. And that's the window scaling. And that is what gives us ultimately how much can be in flight at any given time. So can you configure these things? I mean, does it even matter that we talk about congestion providers and what algorithms they might use? Can they be configured? Sure. We can do in Windows, we can configure this with NetSH or the set net TCP setting, commandlet and PowerShell. In Linux, we can use sysctl for a temporary on-the-fly change, or we can modify this sysctl.conf file for permanent changes. Mac OS, same as Linux, but depending on what you're trying to do, you might need to do some NKE modifications in the kernel, and that takes a little bit more knowledge of the OS. I'm just going to be very frank. I'm not a Mac OS guy myself. I've never done that. But I've played around with the congestion providers on Windows and Linux and tested the impact results of changing certain things. And to be honest, you're not going to notice any difference for a home device on a network, but you might be able to find through modification of the congestion providers in your laptops and desktops and other systems that might support it, an overall change in performance on your network. And that is realistic in the real world. iOS doesn't really give you any access to this stuff. Android does if you have root access, but it's basically, it's still sysctl. So it's still the same as Linux if you do have root access within Android. Okay, so I told you can adjust congestion providers, meaning I can change from New Reno to Cubic to BBR or what have you, if it's supported by my operating system. But does it matter? Well, it does matter. Take a look at this. So all of these at the bottom where you see BICUHIHTHYILSCVG VN WWYE, those are all different congestion providers. That's what all of those are. And this is a specific analysis with 11AC. The blue bars are single hop, so a single wireless hop, like a client to the AP, versus 2 hops, like you're going through a mesh, or 3 hops, you're going through a mesh. Then you see the difference there. But notice that a lot of these are really similar, but there are some that are really bad. And there are some that are worse or better with single hops versus 3 hops and so forth. So yeah, makes a difference there. What about another way to look at it. And this is looking at TCP behavior on multi-gigabit 11AD links. So granted, we're talking about these huge pipes of the 2 gigahertz channel width of 11AD, but still look at the difference between cubic, CDG, which is the CAIA, delay gradient congestion control. I don't know of anyone that has implemented that. So the ones that exist in the real world are cubic and BBR. And look at how much better BBR is than traditional cubic. And by the way, cubic just means that we're using a cubic function in the congestion calculation, which means instead of doing exponents to the power of 2, we're doing them to the power of 3. Okay, that's what cubic means. It's not an acronym. So BBR, though, that is Cisco's bottleneck bandwidth and round trip congestion control. I'm sorry, not Cisco's, Google's. But it has been adopted by many different environments, and there are many different versions of it too. And we'll get to that in a moment. So if you take a look with no loss, yeah, they're all pretty close. Not a massive difference. In fact, BBR is a little worse than cubic and CDG. But as soon as you hit 1% loss, the whole world changes. All of a sudden now BBR is twice as good as the next best and 3 times better than cubic. And you get to 5% loss and, let's just stop playing the game. And again, what are we talking about here? We're talking about 0 changes on any kind of routers or anything at that seamless layer, right? Across IP. This is just the 2 ends and how they're doing their congestion algorithm. And that's the difference that BBR can make. And this is one of the reasons that Google developed it, to handle data center communications, obviously within their cloud and whatever they do to build their entire data center for Google itself, the search engine and all of that. And so when they first developed it, they were developing a solution to resolve problems with TCP congestion in their environments. And so you get to see then that, wow, congestion matters. But hold on, we're not done. Let's look at another source. Now we're comparing different BBR implementations in relation to active queue management, or AQM algorithms. So AQM is the general term for queuing algorithms that are used in routers. So now we're bringing the IP layer back into the picture. And what we're saying is, how does BBR do when you're dealing with different algorithms at the IP layer for queuing? In other words, does the queuing algorithm end up having any impact back propagated, if we can borrow a term from large language models, back propagated to the end device? Is there a difference? There is. So we see cake and coddle and FQ coddle and FQ and pi. And all those are different AQM algorithms. Okay. None of these are directly exactly implemented in most of our routers. So most of our routers use WRED or FIFO for our networks. But we do have cake is in some things like OpenWRT, for example. But I'll talk to you more about that in a second. So what we see here is for downloads and uploads that it even varies within the different combinations of the congestion algorithm at the ends and then the queuing algorithm within the network, that they have interplay. They work together. And in this paper published in PLOS 1 just last year, they called that the golden pair. They're looking for the golden pair, the ideal pairing. And they mostly focused on BBRN, and this happens to just be BBRN, but they did also look at cubic and some others. Their focus was on BBRN because these authors had created this particular implementation of BBR and were trying to argue for how good it was. So they kind of spent most of the time ignoring other implementations of BBR. But they did find the same thing, that regardless of what BBR congestion provider you're using at the endpoints, changing the queuing algorithm for the AQM does end up impacting how effective that is. and it varies for uploads versus downloads. So notice, for example, if you look at the download, the leftmost block here, then obviously Cake is the best. But then when you look at the upload, all of a sudden Cake falls all the way down to the bottom. And so not so good anymore, right? And that's part of it as well. How do your clients interact with the network? Are they transmitting more than they're receiving? Most clients don't, but hey, some do, particularly in data centers. And so all of this comes into play. And then those spanning layer factors then of that queuing information is where we get these different factors that end up back propagating, as I said, onto the end devices. So if you see, we've got examples here just of FIFO, weighted random early detection, which is the most common that's used by the different router vendors for the routers that we use on our internal networks anyway. And then Cake, which is open source and is in open source firmwares like OpenWRT. Cake is actually really ideal for home environments anyway. That's where it works best. And so it makes sense that OpenWRT would implement it. And yes, Cake is not just a tasty treat. It is common applications kept enhanced. I guess they wanted to have it spell a word because that meaning kept enhanced kind of seems, well, I'll just say what we used to say when I was a kid. Seems lame to me. Anyway, WRED is weighted random early detection. See how much fancy that sounds compared to common applications kept enhanced. The WRED is what you see in, at least is the default in many routers that are used in data centers, things like that. You might see FIFO in some of your low-end routers, or maybe even a default in some of your high-end routers. And I'm not going to go over all the textual details of this. You can always go back to the recording and pause and read them if you want to. But the key is that they differ in the mechanism, their ultimate goal, how they do fairness, configuration options, and where they're typically used. So this brings us then to, well, what about IPv4 and IPv6? Do they have any impact? So we talked about TCP congestion providers. What about IPv4 and IPv6? Well, performance is actually impacted very little as far as the difference between IPv4 and IPv6. In a raw analysis of a consistent AP connection. In other words, I'm not roaming, so roaming doesn't get involved. I'm just connected to an AP. If I try to do the same exact thing with IPv4 as I would do with IPv6, the difference is negligible. And in some cases, depending on your network, the reality is that IPv6 can perform slightly worse, particularly when it comes to round trip times. So IPv6 tends to slightly, and I mean very slightly in most cases on your LAN, outperform IPv4 for throughput, but underperform IPv4 for RTT. And okay, I'll try to avoid buffer bloat since it has been commented on as best I can. However, IPv6 has shown some general performance gains which can benefit Wi-Fi as well as wired. And so we see, for example, in scalability, obviously, we have more scalability in our IPv6 addressing. But one of the key areas is in packet processing efficiency. There have been many tests that people have done, but also research-based analyses that have looked at packet processing in routers and things like that, and accomplishing better efficiency, faster processing. And what that comes from is the headers. Okay, so let's go back to our CNAE course, and I've got it here. Let's see here, somewhere. I know it's somewhere in here. Yes, here we go. We've got an IPv4 header. So here's the IPv4 header explorer, and this is just a little learning tool to help people learn them. But take a look. Each one of these is 4 bytes across. So 4 bits plus 4 bits plus 6 bits plus 2 bits plus 16 bits is 4 bytes. And then the next row is 4 bytes and the next row is 4 bytes. So we have 3 rows, 4 bytes each. And you do the math, you come up with 12 bytes, right? So 12 bytes, ignoring the source and destination IP address. So we come back and go into our IPv6 header, and notice we only have 8 bytes. So while an IPv6 header is bigger than IPv4, that's only because the source and destination addresses are bigger. You follow that? So the source address and destination address is just 32 bits in IPv4. It's 128 bits in IPv6. That's what makes the IPv6 header bigger. If it weren't for that, the IPv6 header would actually be smaller. Now, does the fact that it's 128 bits versus 32 bits increase the processing overhead? Actually not, for the kinds of things that are decisional in most cases as far as actual processing. So the studies actually show that the processing is reduced because we're looking at less decision factors. All these parts of the header, where there are more of those in IPv4. And so what that does is it reduces the decisional factor processing in that overhead. We still have to just make one decision related to the addressing. What's my next hop? And processor cycle wise, that really doesn't take anything measurably longer for most of the devices to do an IPv6 address versus an IPv4 address. And therefore, the processing overhead can be reduced. So what are we accomplishing? Well, we're accomplishing reducing our processing delay a little bit along the path. So that's your packet processing. Then there's some enhancements in the security architecture as well, right? So we have improvements of the fact that if we choose to use it, we can include IPsec functionality within the IPv6 protocol. So it's inherent to it. And then network configuration and management is improved under network functionality. Quality of service is improved. Multicast efficiency is improved. And there's some mobility support enhancements that are there, but even though they're there, we don't really get to use them much. And most testing has shown that it really wouldn't help all that much, even if you did. So you got what's called MIPv6 or mobile IPv6, which could potentially be used instead of our controller homing that we used and then tunneling back to our controller as we roam around, which first started with IPv4 and is actually still mostly used with IPv6 too, because it just works more efficiently than what MIPv6 would. And so there's stuff there that, yeah, theoretically could provide some enhancements, but we don't really see it changing much for our operations. The biggest area where IPv6 enhances overall network performance is with your packet processing efficiency. And potentially some slightly lower overhead by using IPv6 within, IPsec within IPv6 instead of as an add-on to IPv4, depending on how you implement it. And then what about some other higher layer considerations? Well, somebody brought up, and I knew you would, QUIC, as opposed to using TCP. So historically, for all of our HTTP communications, and the cloud has really made so much more of our network communications HTTP based over the last decade. The way HTTP worked, right, is you had HTTP over TCP, and TCP handled all the congestion management. Now what we have is QUIC over UDP. So what we're doing is we're taking session and state information and congestion management, taking all of that out and bringing it up a level into the application layer instead of being at the transport layer. And QUIC has shown, which by the way is what HTTP3 uses. So HTTP3, still specifies Now that's a new word for you. You could tell it's my fourth webinar of the week. So HTTP3 specifies the typical HTTP stuff, right? Like get and put and post and whatever. But it also specifies that it's going to use QUIC over UDP instead of using HTTP or instead of using TCP for the transmission. And so that gives you encryption. It's got TLS built in. It gives you session and state management, gives you congestion management, all of that built in. And what the research is showing us and actual implementations, we've got depending on what you look at, 30 to 45% or so of all communications now with web servers on the internet are HTTP3. And a lot of people don't even know that. But, take a look at your Wireshark packet captures. Just do some packet captures while you're browsing the internet, and then go in and take a look and filter on quick to find out just how much is in there. And you're going to see there's a lot in there. You're using Google, you're using Microsoft servers, things like that. You're probably using quick. Where you tend to not see it used as much is the smaller players. So people that are like they're hosting through those hosting providers that they've got 150 websites on a single actual server. Those kind of scenarios is where you're probably still seeing a lot of HTTP over TCP implemented. You get to your big player stuff, you're seeing a lot more quick. In the same vein, so we had DNS, and then we started to do DNS over HTTPS to have security for DNS instead of DNSSEC. And it worked well, but now DNS over quick is showing to work even more efficiently. And so that's obviously important to know about. So the key is, if you're implementing things internally on your network, or maybe you're not, but application developers are, just let them know, hey, we want to optimize the performance of our network. So use quick and HTTP3 for any internal web servers we deploy, or even if they're done in the AWS cloud or the Google Cloud Platform Cloud or whatever. So standardize on that. Implement DNS over quick instead of DNS over HTTPS or DNSSEC for your DNS. Those kinds of things are going to enhance performance wherever you can. And then ensure, I'm just saying, quote, technologies are implemented correctly. So study the performance impact of different configuration options for different technologies. I'll give you an example of that. So VXLAN is a great example. VXLAN's all the craze today, right? Everybody wants to talk about VXLAN, which basically gives you an overlay and an underlay network. And the key here when it comes to performance is you want to avoid fragmentation by making sure your underlay network can handle your overlay network, which means that either your underlay network might need to implement jumbo frames, or your overlay network needs to implement a smaller MTU so that you effectively have smaller segments that are going to fit on the underlay network. And I'm not going to get into all the details of that today, but the point is, make sure you're implementing things correctly to get the results you need, because this higher layer stuff is impacting your lower layer operations. And I've ended a couple times with quotes this week, so why not do the same now? The whole is more than the sum of its parts, but it is also less. It is less because the parts have been constrained by their connections. They have given up some of their freedom to make a whole. What they gain is the special competence of the whole. John H. Holland, Emergence from Chaos to Order, 1998. He's one of the world's leading researchers on systems theory. And there's some really interesting implications of this quote. It's less than the sum of its parts because it has been constrained by their connections. In other words, the whole system is less than it could be because there are some connections that are constraining it. They've given up some of their freedom to make a whole. That's what we do when we create the internet, right? Or even our own internal networks. One individual link in there can be the bottleneck that causes our congestion algorithms to throttle things back to a slow speed, even though every other part of the network works fine with the massive speed we want to use. So when you think about your network, this can be a really good pause moment to really think about it. Yeah, that's true. Am I causing my network to be less than the sum of its parts because of some bad parts somewhere in that network? And that can be an important thing to consider.